Stanford University.
Thank you very much, Michelle. This is the picture that was taken by the university photographer of the Hoagland Prize this year, and I put that up. It was just great. They took pictures on the stage, which were all so boring. But then Linda ran into my wife Lauren and myself afterwards, and it was just one of the nicest. And this is the one that Stanford Report ran with. I was so happy with that. Anyway, let me just talk a little bit about the topic of today and give a sense of it, and then go through the overview of strategies. I teach large courses by and large. Right? Large courses are different from small courses. And in recent years, I've had the wonderful opportunity to teach some small courses as well through the Stanford Introductory Studies program. But my main sort of history in teaching, and what I've done at Stanford over most years, has been teaching courses that are 400 people and above. Right? How do you do that? How do you make something like that work? And how do you manage the difficult parts of that? One of the things I'm going to talk about today is that even though there are advantages that I think all of us know, certainly those of us who have done it, and I'm so pleased in recent years to have had more opportunities to teach small classes, there are real advantages to small classes. But if you use them right, it turns out that there are features that can only happen in large courses, and you can leverage the particular characteristics they have in ways that encourage certain kinds of very educational behaviors. And I want to talk about that here. The problem that we have, and I'll describe this in a little more detail, is that like most large courses, we're dealing with a wide spectrum of backgrounds and abilities. So how do you manage in a large course not completely snowing the people on the low end of the scale, or boring silly the people on the high end of the scale, both of which are terrible things to have happen. You don't want to lose people from the educational pipeline, because a lot of the people who are not getting it as quickly as others will get it if you can encourage them along. But more, I think equally importantly, you don't want people to decide that this is just too mundane, not to be challenged, to fall asleep in class, or not to come to class when they have the ability to do something better. So when faced with that problem, we wanted to think about how we could solve it at Stanford. And there's several different ways. First, you want to try to minimize that variability. If there's a mechanism by which you can segment out, if the class is large enough, into separate tracks, people of more or less the same background, not necessarily the same ability. I'll talk about that in a bit. But try to get some sorting. You can have a more homogeneous population, and that helps. Obviously, this is something that you can only do if you have a large population. If your sort of quarterly count is 400 or thereabouts, then you can afford to have a couple of different courses that divide that population up. And if you can find a way that self-selection will work to sort it into people of similar ability and aptitude, then that causes some of the problem to go away. But that's only a piece of it. The other thing that I think is really important is that you want to be able to define thresholds for a particular quality of work and stick to them. One of the difficulties in a large class is if you decide that you're going to curve it rigidly, you've forced it into a mode where many people are going to be unhappy with that course. So one of the first things that I talk about in those large introductory courses that I teach is that this course is graded without curves, at least in the main. It's always hard to tell on an exam how hard the exam was. So the exams are scaled, but nothing else is. And if everybody does enough work to get an A, then everybody will, in fact, get an A. But then you have to set that bar extremely high. That's a wonderful sort of covenant that you can establish with the students. We're going to make this really tough, but if you do it, and we will support you every step of the way, as I'll describe, then you're going to do well in this course. That provides a much better incentive relationship than I think exists in many large courses. So that was important. I wanted to provide extensive opportunities for extra credit work. I can't run the class for the top end, because then I will lose the people at the bottom. Therefore, I'm forced in this distribution of abilities that we see in the class to run it. If I'm teaching 106A, in fact, the course that's the slower of the two tracks that we offer, I'm probably aiming not even for the median, but maybe a little below it. I want to get that's where I'm trying to teach. And then for people to exceed that particular standard, they have to do a little bit of extra work, but I make those opportunities available. And most of this talk is about the extra credit opportunities that we've made available, because what I've discovered in talking about this in other contexts is that they are mappable to a wide number of fields. And there are some insights that we've gotten in putting these together that I think might help if you're trying to design some strategy for dealing with that kind of imbalance in the course. They should all encourage creativity and initiative. They should also be relatively open-ended with respect to this set of requirements. When we write assignments, for example, when I write assignments, those are extremely detailed. People know what's expected of them. I also will write on the assignments, here's some things you might try, and those are not detailed. Partly because I don't want to put any ceiling on what people do. I want them to run with that opportunity as far as they can. You might try this, and I describe this, whatever it is, in a sentence or two, and hope that people will spend as much time doing this, whatever it is, as they spent on the entire rest of the assignment. And many Stanford students will. And one of the things that we've done, partly because we are forced into it by the economics of the field, I mean, it's true at every university that I know, that the undergraduate teaching at the introductory course, all the teaching assistants are undergraduates. The reason for that is that there aren't enough graduate students who are willing to do that job, and the number of students taking those courses is huge. So John Hennessy, for example, was an undergraduate TA in his computer science course when he was at Villanova, and he says that's the only reason he's in teaching today. I was at Harvard. It's true everywhere and has been. We decided at Stanford to make a virtue of necessity and really train those students to be wonderful as teachers, so that our undergraduates, many of whom are here, who have worked as section leaders, have a chance to learn about teaching. They have a chance to become involved in that piece of the Academy's mission and really do a wonderful job in providing not only sort of role models almost at the student's own level to pull them forward, this what I've called stepping stone role models, which turns out to be particularly good at encouraging diversity. If you're looking to try to increase the number of women or the targeted minorities, having people who are close in their own age are, in fact, more effective role models than people who are 30 years out. It's just very interesting to look at the statistics on that. But it works in general as a way of pulling people along. But it also provides the possibility for us to develop a giant safety net for our courses. When students are given a bar that's really high, they've got to work to meet that. There's a huge incentive to do it. If they are allowed to founder along that path, then it's not good. So what we do is we have this wonderful core, usually of 40 to 50 undergraduate TAs, not only in the courses, but in the big terminal room in Treseder, so that whenever you have trouble, you can get help. That mechanism makes it possible to drive the courses at the speed that we do. So those are just some strategies that we've used. I need to talk a little bit about the courses. Here's the way that we divide up the courses to get more homogeneity within the populations. We have 3 tracks. There's a general education track, which is CS 105. These numbers, by the way, of student numbers are last year's numbers. It's gone down considerably, described in the last few years. The largest of the tracks is this track, CS 106A and B. That's a 2-quarter sequence, which covers the material in an introductory, what is usually a 2-semester course at another institution, and gives people a solid foundation that would be good for majors. It would be good for electrical engineers and other engineers, but it's good for everybody, as you'll see. That's by far the largest of the tracks. But to get the high end of the distribution out of that population and make it more survivable for the regular folks who haven't been programming since they were 4, we have CS 106X, which is the accelerated version. Those of you who are watching the undergraduate program may have noticed that chemistry did exactly the same thing this year. The chemistry intro sequence is now Chem 31, 31AB, 31X, just like our program to provide that same sort of separation. It's been wonderful for us, and we use it elsewhere in the curriculum. By self-selection, you get the hotshots in here so that they're sort of competing at their level, and the people who are a little less convinced of their own skills in that course, which is great. Enrollments have been an interesting problem. Here's some enrollment trends. Like everywhere in the country, they were going up. This is the term time enrollment. We were actually including, if you include summer session, over 1,000 students a year in CS106A. But this is a better gauge at what fraction of the students at Stanford were taking 106A. At the 850 level, that's about half time averaged. But something happened, and it fell. I can't get the last couple of years. We're using new PeopleSoft software, and it's really hard to get good data. So that's what I've got. And just so you can compare it, that's probably related to the reason. And maybe this will, over time. And NASDAQ is a leading indicator on computer science enrollments. Our number of majors has fallen about 30% since the NASDAQ crash. It's well over 50% at many of our comparable schools. I mean, it's just a nationwide collapse, which is very interesting to try to work with. But when it was at its height, which is when I was doing most of this work, we attracted essentially all of Stanford. Here's the eventual majors of students who graduated from CS106 in the mid-90s, from 106A. 106X, the accelerated version, more people went into computer science and engineering. But only 6% of my class is going to end up being computer science majors. The rest are going to be doing something else. And in fact, some of them are in EE or other engineering. And if you take the science piece of that, it's about 2/3. But I have almost 20% of the people who are going to be doing social science and humanities and other things. It's a wide spectrum. And I wanted to encourage those people to be in that class. It was one of the singular, I suppose, signature aspects of the Stanford curriculum was that we tried to teach an introductory computer science sequence that really did have broad appeal. And it did. I mean, it was, as Michelle said, it was the largest course at Stanford. So that gives you a picture of the population that we had. The other thing, yes?
How did you find that out?
How did I find that out? Well, under of course, the old data technology that we had, you could do those things. What I did was I took the population from computer science in CS106A in 1 year. 3 years later, I saw what the students majored in, and then I made this graph, So all very easy. But that's harder now. Progress. The other thing that I need to talk about is a little about one particular aspect of the software development trade, if you will, or programming as an intellectual activity. It is one of the most widely varied activities in terms of productivity and ability of pretty much anything we know. There are other things like that. I mean, mathematics tends to be like that. Writing good novels is like that. Being able to direct a movie. Being a professional sports player. The difference between this person who's sort of good and that person who's really great is extraordinary. And that happens at the undergraduate level, too. Here's some statistics that just give a picture of this. It's been known for a long time. There's a landmark study back in 1968 of working programmers that showed for people with the same level of education, same experience, that you would get perhaps 20-to-1 variations in productivity measures. In other words, how much code a single person could generate. It's not like, bricklayers where all of the individuals are created more or less equal. If you get people who are on the high end of that distribution, they can do a lot more. Moreover, those measures turned out to be extraordinarily well correlated with other measures of quality. The fastest programmers were also the best ones. They had fewer bugs and things. There was just this, when you expanded it out to make a more broad quality measure, that in fact increased rather than decreased. All the recent studies confirm that variability. And when I talk to people in Silicon Valley today in the computer forum that Stanford's computer science department supports, they argue it's much higher than that. They believe, no one bats an eyelash if you tell them that they can hire one person and relative to another person with the same degree qualifications, that first person can be 100 times as productive, which is part of why you get this frenzy in the hiring pool. You really want to find those people. Well, that's an important aspect of this field. I'm going to be talking about this tonight for a State Department conference, so where they need to understand this as IT planners in different countries. But it's also relevant to education because you see the same thing in classes. Even if you factor out prior experience, and sometimes prior experience doesn't help at all, you'll find that a lot of people who have been doing this in a self-taught way can internalize extremely bad habits that are very difficult to break. But the people who somehow seem, I believe, temperamentally, the studies of the psychology of computer programming show that this is not something that correlates well with how much mathematics you've had. In fact, there's a wonderful study that came out in the 1970s that showed that performance in introductory computer science courses was negatively correlated with the amount of science you'd taken in high school. And I can explain that seeming paradox if you need one, but they're just, it's not anything. It has to do with a certain sense of determination. If you will not be beaten by a computer, if you have wonderful fun frustrating yourself into oblivion as you work on these bugs, and then it works. If you can see that epiphany and get joy from it, that temperamental quality can make you a very good programmer. If you give up as soon as the first frustration occurs, you won't succeed. And so there are these sort of factors in one's temperament that seem to apply here. I'm convinced, although I haven't done this experiment, I'm not sure how I would do this experiment, that if I just on the first day of CS106A said, here's the final exam, take 3 hours, here's the book, go do it, that the top 10%, even of people who had no prior background, would be able to outperform on that day the low end of the distribution at the last day. Because it's an open book exam. Oh, this sort of looks like that. I'll write just that down. And you get enough partial credit that it would be a lot better than the 0s and 2% we get at the end of the quarter from people who just can't get this stuff. There are such people. And that variability makes it particularly hard, particularly since it's difficult to understand how one might predict it. There have been hundreds of papers in the literature about how one predicts programmer performance because every university is trying to optimize that. We could talk about that in the questions because there's some interesting ideas that came out of it. But that's what we've got. We've got this population that we can't predict. It's not correlated with experience particularly. There are going to be some people who are just really good and we can't leave them behind. So I do several things. The most visible is that I have contests. I have 3 contests a quarter in CS106A and B. They're fairly high profile, and they occur at very well-spaced points in the term. I want, in both those courses, to have a contest in the first week. That's tricky. How do you do that? Well, fortunately, when I've been teaching, and again next quarter, we're going to start the course with something called a micro-world or a pre-programming exercise. Some of you may have seen it. The standard one in its day was Carol the Robot. Carol the Robot is that robot in the bottom left corner. Lives in a world that has walls, these funny things called beepers, which can be used to signal particular activities. Carol can't walk through walls. Carol is extremely brain damaged in its ability to move. This is the Microsoft model. It can turn left, but it can't turn right. So the first thing you do is when you tell people, well, how do you turn right? How do you do it? Turn left 3 times, and that's what you have to do. And this is that notion that of programming is you get that to happen. And the kind of thing that we do, this is probably the most sophisticated, it's certainly the most sophisticated example in the text that goes along with this, is solving a maze. This is solving a maze by a right-hand rule. Carol is going to just keep turning right and see if it can go that way. And when it finds the beeper, Carol decides that it's done. This is good problem solving through programming, and it's a very simple environment. It works well for everybody. And you can learn it in 1 hour. So right there, we've got something where people can start to use this. Well, what do students do? Here's a couple of examples. Here's the risk game that Kimberly Goodwin did. This is Carol now. The world can be resized. Carol still points in a direction, but it doesn't look like the robot anymore because it doesn't fit on the screen. Kimberly decided she was going to program all of risk, right? And eventually she changed her mind, and she's only going to program risk with continents as countries instead of the whole thing, and only 2 dice for the attacker and only 1 for the defender. But my God, it actually works. And here we see Carol racing around, figuring out which country is attacking which country. They are all randomly set. Given that there's only 1 green country, if South America attacks North America, this game could be over very quickly. This won in one of 2 categories. This won the algorithmic category. There's also an aesthetic category, which I'll show you in a minute. The reason that this is hard as a problem in terms of problem solving, I can illustrate that by talking about one of the things that's going on here. Kimberly decided that what she wanted to do was have the most powerful country attack the least powerful country. Modern diplomacy. And the way you figure that out, each one of these little things that looks like a single beeper is actually a whole column of beepers. You can stack several beepers. That's the number of armies on that continent. Carol can't count. Carol can't do anything. It can just pick up a beeper and put down a beeper. So how do you tell who's stronger? Well, it turns out through this wonderful technique called recursion that you can copy a pile of beepers from up here down to the bottom row, which is what Carol's doing when it's running back and forth up there. So we can copy to the bottom row all of the piles of beepers. Now, how could you tell which pile was biggest if you can't count? You notice that Carol's running back and forth across that bottom row a lot? What's it doing? Well, you run across, take 1 away from every pile. You run back, you take 1 away from every pile. The first pile to go away is the smallest. The last pile to go away is the biggest, right? So in an environment that didn't have any of these things, Kimberly was able to get this going. So this was a great example of a Carol program. We also have a category called aesthetic, the people who can tell the best story using either the Carol world or the graphics context, which is the next one. You'll see the example of a aesthetic graphics contest. The one I chose for the aesthetic example here, I just love it. Most people don't think of it as being particularly aesthetic. There have been wonderful examples that would please the English majors. There was Carol, Prince of Dotmark, which told the Hamlet story in Carol as it wandered through, and it starts out in the parapets and ramparts. It was great. But this is the one that I thought was just amazing. This is an animation of the last game between Deep Blue and Garry Kasparov when Kasparov lost as the reigning world champion against the computer, the IBM Deep Blue computer. Now, that sounds like, wow, that's pretty algorithmically hard. How could you do that in Carol? Well, you don't. There's no chess playing knowledge here. It's all written out exactly in order. Well, make this move, make that move. It was well done. But all it is just going through a script that's showing you what's there. So it's essentially running a movie. But you can actually watch it as the game plays. And Kasparov is going to get wiped out on the black side on the top and lose the supremacy of the human championship to a machine. There's a castling move. I don't know if you saw that. The little X's which appear from time to time are capture. There was a check when the plus sign appeared. It's really quite detailed. And as I said, the code was extremely well done. When you look at the code for the main program, it's the score of the game. As chess players would write it out, the procedure names are the same as what a chess notation would have, so that anyone who knew about chess could read that very, very easily. think we're done. That was where Kasparov resigned at this point. King's out in the open. It's all terrible. Okay, so that was an example of an aesthetics where the point of the judging, however, is that I don't do the judging. The judging is done by all my section leaders. There's an army of them. They look at all these, they vote, there's a ballot, and they figure out which one. So there's a certain independence of that. It also gets the section leaders involved in this aspect of the course. The next contest is a graphics contest. And this is a very old one in a time before long before the modern graphics library, but it was still quite good. You can't really see. There's this dark part here is actually gray. The color is a little less good on the projection. Many of them have to do with whatever I've done in teaching. This one was an example. This palm tree is done with just arc segments, and all of this. This is a winner of the aesthetic category rather than the algorithmic category. It just was amazing to see what people were able to do. This is in week 3 of the term. They learn more by doing this assignment than most of the students learn in the entire quarter. I'm sure of it, because what you have to put together to make something like this work. So anyway, I ruled over a vast desert land called Ratumak Isins, which you can probably figure out if you work at it. Many came to this land lured by lucrative careers. Well, but after they arrived, I had them build pyramids. Pyramid was one of the section problems, but it wasn't this pyramid with colors. It was just the nice little pyramid with blocks stacked on top of them so they could get used to for loops and so forth. This was a 12-minute story. I've only done the 2 slides from it, in which I'm eventually, this is my citadel, and it gets destroyed by a fireball, and everyone is free. This is, people have good fun with this. I have good fun with this. That one was sort of eclipsed by one I will show you more of. This is the 2001 CS Odyssey, which I will just have it run. It was actually much slower, and I've deleted a lot of frames. All the monoliths are my own books and things like that. And I don't know if you remember the story well. This laptop is, of course, not the film. Here's the bone that's being thrown up and then transitions into Strauss's theme, where we have the little ship docking with the space station and so forth. It's running very slowly. But this one's certainly worth seeing. There's the situation on the moon, and you can't see the borders of the monolith, but that's my textbook. The reason that this is interesting is that none of this is done with images. Images are not allowed, so you can't go to Photoshop and make something. All of these are drawn by drawing the geometric figures, which is amazing when you look at the next one. Here, there's not that one. I think that's just amazing. It's all circles and arcs. That's Dave coming in through the airlock. This is Carol 9000 being blocked. And now we have the trip through the Stargate, where you remember all the special effects in Kubrick's day, which were, of course, not what they are today. But here we have the psychedelic trip through the Stargate. This is about half as, I'm showing you something that's a lot less than half as long, but half as many of the frames as in the original movie that I did show the whole thing in class on the day that the contest winners were announced. And people just go wild about this. They're just so extremely happy that their material is getting showcased in that way. And the other students, I think, vicariously get real joy in having watched this happen. I have some survey results to show that. I don't know why. It's definitely on the slow end here. But we're almost done with this one. And then the final scenes were of the Star Child. A second. There we have the Star Child. And then everyone wants to have, their name in light. So this was directed by Sebastian Davis. I love this. This is worth the whole teaching of a course. Every piece of preparation you do is wonderful if people are going to produce this kind of thing. And lots of people, as you'll see, produce this kind of thing. Maybe not at quite this level, but they're really wonderful. The last assignment in the course, when you do a project, or when you do a contest at the end, because the end of quarter is so busy for people, it's really hard to do something separate. Both of these are out of band. You can just do something if you want that's completely unrelated to the assignment that people are doing. It has to be, because it's much more sophisticated than any assignment you could do. The last assignment I did for many years in CS106A was having people write a text adventure game where you're doing all these things that you did in the very early games, entirely text-based. So, follow stream, down, open, pick, lock, do this kind of thing with 2-word commands, and you would get through an adventure game. That was a nice assignment. But I told people, partly because, that was the years in which Myst came out, and people would come into my class and they'd say, can I program Myst after this? And I'd say, well, probably not. It's a pretty sophisticated piece of code. But I was being insufficiently ambitious. The average student couldn't program Myst. And even perhaps the 10th percentile student, 90th percentile student couldn't have programmed Myst. But maybe the 99th percentile student could. And if I gave that as an option to, the contest is extend this adventure game to make it as exciting as you can possibly make it, then we have those opportunities. And here's just one adventure game that came in the last time I taught CS106A. It has all the text part as it's supposed to, and we're now in the Gryffindor common room. But it's all done using mouse commands, just like Myst and Ribbon and Excel. So if I look down at the chessboard, I discover that Ron's left the piece there, which I can now add to my inventory and then come back. I can go into the bedroom. This is a huge, huge geography. I'm only going to show you a piece of it. But one of my favorite puzzles was in this room. You start clicking around everywhere, and you click and you open a messy drawer. And you think, oh, what a nice touch. But if you stop there, you miss something. The drawers are different. And that drawer has a wand in it. And if you don't find the wand, you can't solve a problem later on. And so we can close that, go back to the common room, go out into the hall. And there's wonderful stuff here in addition to the disk. Oh, you can't really see this. That's too bad. It's wonderful on here. But in the bookshelf, which you couldn't see, there's a book that you can read about firefighting potions, and you need that later on. So it has a lot of the play action of one of those professional games, and people, I think, really enjoyed this. So there's some examples of that kind of thing. So what do they get for this? What's the incentive? How do I get people to, I would guess 10 to 15% of the class enters the Carol contest, because it's pretty easy to put an entry in. It's smaller for the later contests. There's no way of counting the number of entries in the final adventure contest, because your submission is an entry, and then the section leaders sort of go to look at how much extended it is and then forward me their best ones, and then those get. So there's no set of particular entries. I would guess that 10% is the average contest participation rate, which means if your class is 15 people, it's not going to work. But if your class is 400 people, the law of large numbers guarantees you that it will work statistically. You're going to get somewhere in the neighborhood of 40 to 60 entries, which means that some of them are probably going to be good enough. So here's what I do. The first place prize in each contest for each category, so both the aesthetic and the algorithmic prize, is 100% on the final exam. That's a really good incentive for people. It's also really cheap. In fact, it saves labor. Not much in a class of that size, but. And so you wonder, well, how are people going to react to this? And I'm not sure how people would react to this unless you shape their reactions for them. When I talk about this, I say, that's great. It takes a lot of the pressure off the end of the quarter, if you happen to win this. But let's think about it from the people who aren't even entering. The people who win these contests could do really well on the final exam. They've done all this work. I just took the best student out of the curve. And that's pretty good. They like that. And there's more. But that's not the real. Oops. The real thing is that winners rise out of obscurity. They're in this giant class. I don't know the names of people. I mean, the worst thing that ever happened in this story that, I don't even recognize the people who sit in the back of the lecture room in Hewlett or in the big Temperament auditorium sometimes. I was at the bookstore in the third week of quarter one time when a student was buying my book and they didn't recognize me. Now, that may have been that they hadn't actually shown up in class, but, there's this funny situation when the course is that big that you don't have the individual interaction. But if you provide a mechanism by which people can play for that interaction and become noticed, then they do. So here's some of the things that I do in that. All the winners and runners-up and honorable mentions received certificates. This was the aesthetic contest for the 2001 thing that you saw. Again, it's better here. If you can't see that picture, that's Escher's drawing hands, which is a nice, there's something relevant to each one of the contests that I give out. And so there are about a dozen of these for each of the contests. So people really get the sense that, that they got noticed. I do spend half of a lecture day demonstrating the top entries, and people go wild. They clap. People stand up. They come and get their certificate, and I think there's a real sense of camaraderie and the pleasure in knowing what people as students can do. It's worked out really well. The winners come to dinner the following quarter, all in a group, so at our house, and that way they get to know me a little better. And I send individual letters to everyone saying, this was great work, and also to the A+ students in the class, if there are any, not usually, and say, if you ever need a letter of recommendation, I will write one. So keep that. Other faculty members in computer science who have adopted just that piece have said that it changes the relationship that they have with their better students immeasurably. You've just said, you've taken the trouble to write a letter, put a stamp on it. It's not an email message. It comes in, it's on letterhead, and they say, gosh, someone really noticed, and there's some tangible benefit from that later on. Yep.
How much do you say in advance about what you're going to do?
Oh, I don't say any of none of these things, I guess, except the top one. All they know as an incentive at the beginning is that they're going to get 100%. But the others might not be obvious, or it might not be incentives. And I don't want to make it seem as if we're really sort of sorting people in this way. But all of these things are sort of little bits and pieces you can add to encourage those top students to go on and do more work. And we have a lot of students in CS who take the introductory course thinking they're going to be English majors and like it. Nothing wrong with being an English major. I mean, it's just that was not at all the point. I'm in the building that used to be computer science. This was our building, and then English took it over. But I'm not. There's nothing there that is relevant to that. I'm married to English people. It's wonderful. The point is that some people who really like this can get turned on by it. My favorite story is of a young woman, Marissa Mayer, who did win one of the contests. It's not one of the ones I've shown you. She took 105 from me. If you go back to this picture here, which I can't see. And see, she took this course for general education major. She was going to do creative writing, and still does some. But she liked that, so she took this one, also from me, because I happened to be teaching that the next quarter. She won the contest there, went on to get an undergraduate degree in symbolic systems, a graduate degree in computer science, and a master's degree, and become employee number 9 at Google. So she had a good time. So the last things I want to talk about is, well, what are the possible downsides? Oh, no, one more thing first. There's some other ways that we do this besides the contests. I want to show the grading scale that I use, and most people in 106A use. It's written not in terms of points, but in terms of buckets. Underneath, there's often a point scale to make it easier for the students to grade. But what we're really aiming for is a check plus. That's something that meets the requirements, which we've detailed on the handout well. That corresponds roughly to an A. I don't tell students what these correspond to. That's not the point. That's just to tell you about it. That's a check plus. There are very few grades in the system that actually get given out. If they meet the requirements but have minor problems, that's sort of an A minus-ish thing, but we call it a check. It's mostly there. And maybe they don't do as well. Yeah, it's a check minus. That's probably 90% of the grades, with 75% being in one of these two categories. Right? So there's not a lot of variation. We're not trying to be particularly precise here. When I've argued this, what I'm doing is I'm trading off precision for accuracy. If you've got 100 points, you're incredibly precise. You know, there's a 66, which is different from a 67. But I'm not going to stress any accuracy there. You know, I don't know that the 67 is, in fact, better than the 66. If you reduce the number of gradations, I can have much more confidence that that assessment is accurate. But there are other grades. You could really screw it up. You could, why did you turn this in? But, you know, it's not even close, and that's a minus and a minus minus. But the scale is symmetrical. There's also a plus. It's got to exceed the requirements in some ways, which means you had to take my list of possible additions and add something. And there's a plus plus. This was described by my colleague Nick Parlante at one conference probably a decade ago as the assignment that makes you weep. And people remembered that at the Symposium on Computer Science Education for years afterwards. I note in the parentheses here that it has to be juried. In other words, a section leader can't give it. You can't assign a plus plus grade. You have to bring it to the faculty member, to the TA, and they have to agree that this passes muster as that superstar program. People try really hard to get those. And, you know, there were many years where I gave about 2 or 3 a quarter. And then one year, I don't know what happened, but I gave about 15. And I didn't change my standards at all. You know, I just got a really good, energetic bunch of students. This is quieter. It's not, you're not putting yourself out in a contest sort of environment. It might appeal to a different set of students. But it does really give them an incentive to move forward. Okay, so a couple of things here. I thought about ways of, well, what about all the students, the 90% of students who don't enter the contest? I've claimed, I will show some statistical data to support this later, that the other students like it vicariously because, in fact, it makes for a really fun demo period in class. But I do have another incentive that occurred to me fairly late on, I mean, probably 5 or 6 years ago, that works remarkably well. One is to provide another incentive. I'll do that one first since I started to talk about it, and then go to the other one. If you enter a contest and get an honorable mention or runner-up, you don't get the 100% prize. You get 5 points. If you get an honorable mention, you get 3. If you enter at all, and we deem it a serious entry, you get 1 ticket in the end of quarter lottery. So we run this when we announce the adventure contest winners. Here is the set of tickets with initials for people so they can find themselves, and we make them unique so that there was 2 CHs here, so we had to add a second initial there. And the number of entries, you know, whoever CHA is has, in fact, 5 tickets from whatever combination of events, so they have more chances to win. And the prize in this raffle is also 100% on the final exam. And that way, you know, even the people who are not as strong have at least that opportunity and that incentive. But what's so fun, and the reason I wanted to show this, is you could put these in a hat and you could draw one out. There's no drama in that. I have already, inside the program, sorted these, and I know which one is first in the list. I don't know, actually. The computer knows which one is first in the list. What I do is I eliminate them. It's Calvinist, right? The answer's already known, right? But, you know, and people can say, oh, no, you know, you could think of it from this perspective. None of mine have gone yet. I'm now as high up on the list as that person. Oh, no, one of mine's gone, you know. It's just, the other one gone. But at least, you know, and so, you know, the chances still go to the more energetic people, but You can't believe the tension in the room. This is, round about this point, it's really getting palpable. As everybody who's entered a contest is, of course, there. Okay. So that was a nice little piece of software. The piece that I introduced, in fact, more recently than that, was a way of trying to encourage people to enter these contests by appealing to class loyalty, not class in the socioeconomic class, but the fact that new students who predominate in this class and sophomores might feel a little bit of, you can just build up some structure. And I took my lead from Rowling. And here, for example, were the points that were accumulated, same point scoring system as on the final exam, the last slide, rather. And the class that has the most points relative to the size of its numbers. See, most students are first years, so Frosh are dominant, but you have to get more points relative to that size to get the size of the bar. So the junior class was, winning, and they got to have the Gryffindor title. You see, Ravenclaw is second, and Hufflepuff, and then, if you have to be Slytherin at the bottom, you want to get out of that. So by the second contest, the first years had decided, no, they're going to really work, and they almost, on the final contest, caught up with the juniors, but didn't quite. So, that provides a sort of collective incentive for the whole thing. I still worried that this might be unfairly prejudicial against people who really didn't like competition, and that might have correlations with gender, for example. So I did some surveys. The first contest I did ever, by the way, was when I was at Wellesley. And that was one of the most effective ones. My prize then, I hadn't thought of the 100% on the final exam. I actually sent 2 students to Bermuda. And boy, did they go after that one. So here was a survey I did. On the survey, I realized I didn't put it on the slide, but it's a little over 200 responses one year. So I could get some information about what the background was. I was looking particularly for possible gender correlations. I had other people review and grade the answers to the reaction to the contest presentation, so we could get a sense of whether they were positive or negative about that presentation. Most people were quite positive, the 64% to 8, and for people where you couldn't determine what answer, the answer that they wrote there just didn't give, it was either too mixed, or the people I had scaling that answer couldn't report. But you see that huge factor of 8 difference in the positive negative, so it seems to be. But what about correlations? Well, it turns out there's only one correlation that was statistically significant. There's no correlation whatsoever on gender or background. If you entered a contest, you liked them more. I could have guessed that. And if that one hadn't come up, then I would have wondered about the validity of the study. But that's the only one that's there. Everything else is way down in the noise. And so I've presented this at a couple of conferences now. I have a paper from the big CSE symposium. And I know it's being taken up at other places. And I've talked to a number of people who've been trying similar things. I mean, computer science is often easier because we have the ability to generate our own virtual worlds. But there are probably ideas that you could take from this in any of a number of disciplines. It went on longer than I thought, but I have some time for questions. Yes?
So this looks wonderful for motivating, the top students in their work outside of class. Mm-hmm. But how do you format your lectures so that they're not bored? Because you have to talk to everybody at the same time. Mm-hmm.
Well, I mean, it's a difficult thing. I mean, I try to include in my lectures a lot of color, quotes. I mean, I never plan them beyond, knowing how I'm doing. And something will come up, and there will, of course, be fun examples and really good lecture slides. I tell lots of stories. I could probably show some of the stories here. One of the ones that I just love is when we're doing random numbers. A couple of years ago at Don Knuth's 64th birthday party, more than a couple of years ago now, one of the speakers was Percy Diaconis. I think people know Percy. He's a statistician, but he's also a magician. He was traveled for 14 years. He left school at age 14, never went to college, came back, got his PhD in mathematics, won a MacArthur the first year they were given. You know, he's a very bright person. And anyway, he was asked to evaluate shuffling machines in Las Vegas. He's a magician, so he should know something about this besides he's a preeminent statistician. And he tells this wonderful story about shuffling machines. There was this completely bogus shuffling machine that this casino was being asked to buy from somewhere, which didn't, in fact, randomize the cards. And it turns out that the argument was easy enough that I could make it in class. So I built a model of the shuffling machine, and we show that. And top students are really interested. There's a story there. You know, people have talked to me, and they say, well, I just love the Shakespeare quotes that just get thrown in there from time to time. And I don't know what it is. You appeal to different people in different ways. So that's a whole different talk that I wasn't, you know. But someday we can talk about what I do in lecture. I'm not always sure I know, but it seems to go okay. Yep.
So one thing that I've noticed through my coursework is that the amount of feedback I get on assignments makes a big difference in my motivation. So I wonder if you...
Well, we do that in our course the following way. Again, we have undergraduates doing the sections. And what we decided we would do long ago, early 90s, was we were not going to try to economize on this. Undergraduates are a lot cheaper, mostly because you don't have to pay tuition, right? And for graduate students, you have to pay tuition, and undergraduates have a cheaper scale anyway. So one could imagine that you could have the same number of staff for about half the price. But if you instead decide you're going to hold the cost constant, that means you can have twice as many people, which means you can have smaller sections. So we have, the sections are a little larger this quarter. What are there, about 15? But our target, because there's actually an increase in the number with the variability in enrollments. You never know how that's going to come out. But what our target is to have 10, and it will drop to about 8. And so that's what we're trying to staff for. And that's a small, good interactive section. But what we do also is that the assignments are graded individually in this mechanism that we call interactive grading. You turn it in, the section leader looks at it, marks it up, and then goes over one-on-one with you what the problems are, just like in a writing tutorial. And the idea is that that way people are forced to look at it. And the other thing that the bucket grading system does is it means that people aren't, you know, playing for points most of the time. You know, if we have this grading system, you know, check plus, you know, that's different. You know, if somebody's going to argue with you for hours about whether it's a 70 or 72, you know, but this is a lot easier to justify, particularly if the undergraduate graders are peers and sometimes actually younger than the students that they're teaching. It's really important to have the ability not to force them to be in that complicated, combative grading battle. Others? Yes?
This is really away from your focus, but I'm curious about the explanation of this negative correlation you mentioned between CS performance and high school science.
Well, my own, I have no way of judging whether this is correct, but my own belief is that that may have measured whether or not they took a high school computer science course. Obviously, the number of high school courses that they take will correlate positively with whether they took a computer science course. High school computer science courses are generally very bad. So if they were more likely to take that, they'd be less likely to. So I may have had something, or they would have learned bad habits, since high school teachers don't, you know, if you know how enough computer science to teach it, you don't work in high schools, by and large, because the job market has been tremendously good most of those years. Michelle.
So, Eric, one thing I didn't mention in the intro is that you're a consultant to Bermuda on their CS curriculum, and I just wondered if that's a coincidence with the fact that the Wellesley Prize was a trip to Bermuda.
No, that's entirely a coincidence. I had never been to Bermuda before we did this. I mean, I figured, you know, I was sort of the only person. At Wellesley, as this was true in many places, the computer scientist department had 3 times as many students per faculty member as their next closest rival, not the average, so the next, because we were understaffed and you couldn't hire anybody because, you know, this field is very bizarre. I mean, in 1984, which is the year that I took that statistic from, the professional society estimated that there were 7 job openings for every applicant. So most schools don't hire, right? It's just the way it was. And so we were overworked, and I figured the only way I could enjoy a vacation like that was to do it vicariously and send some students. So that worked out really well. It was just, I mean, and, you know, that's Boston area. Bermuda's relatively warm. Here it probably wouldn't work. You know, why go freeze in Bermuda? So, yeah. I mean, the Bermuda project that you mentioned is really interesting. I mean, one thing we could do is, I don't know if we have to get out of the room immediately, but if people want to stay, because I just gave the talk, there's a 6-minute movie on the Bermuda project, which is just wonderful to see. So we could show that. It's on the laptop, I happen to know. So, but I'd let people go before I subjected them to that. Other questions? Okay.
Thank you
Thanks.
so much.
For more, please visit us at stanford.edu.